Good morning, good afternoon, or good evening, everyone. Welcome to another RTDS Technologies User Spotlight Series 2.0 webinar. Today is episode 4. I'm Katie Sidwell with RTDS Technologies. We are a real-time power system simulator manufacturer based in Winnipeg, Canada. And today we're showcasing the work of some of our product's users. We have two very exciting presentations today about out-of-step protection and electric vehicle charger testing. And the first presentation actually includes a demonstration as well. So you'll see a real-time simulation demo via screen capture of our simulation software. But before we get to that, there's a few housekeeping notes. Firstly, if you're listening to this webinar recording will be made available to you. It will be uploaded to our YouTube channel so it can be easily shared and viewed that way. And you can also send this webinar to your colleagues who might not have been able to make it today, and they'll be able to log into the webinar platform and view it on demand. And the Q&A panel can also be used on demand, so if you're viewing this after it's already aired, please don't be shy, you can still ask questions and we'll get back to you by email. In terms of agenda today, we'll have two presentations that are about 20 to 25 minutes each, and at the end of the session, after both presentations are finished, we will do a live Q&A session. Now, all throughout the presentations, you'll have the opportunity to submit questions via the Q&A widget. So that widget should be near the top left of your webinar platform screen. Myself and our presenters will be answering your questions as they come through, and then for the live Q&A, we'll choose a few questions to go into more detail on. We'll also be releasing a webinar Q&A document after today, so you'll have access to the written answers to any questions that we didn't get to live. All right, without further ado, let's get into our user presentations. Our first topic is hardware-in-the-loop testing an adaptive out-of-step protection algorithm based on wide area measurements from Delft University of Technology. And I'm happy to introduce our presenter, Marco Tealane. Marco received his BSc and MSc degrees in electrical power engineering from the Tallinn University of Technology in 2014 and 2016, respectively. From 2019 to 2020, he was an academic visitor at the Delft University of Technology, where he was working on out-of-step protection in the Intelligent Electrical Power Grids group. In the past, he worked as a protection engineer at the Estonian transmission system operator. Currently, he's on sabbatical leave. He works at TU Delft and is pursuing a PhD degree in electrical power engineering at Tallinn University of Technology. His research focus is on power system protection, power system relaying, and wide area control. Please welcome Marco Tealane.
Thank you, Katie, for the introduction. My name is Marco Tealane, and the topic of my presentation is HIL testing an adaptive out-of-step protection algorithm based on wide area measurements. The outline of this presentation is as follows. First of all, I will discuss what is an out-of-step condition and what do we use to protect against this condition with the conventional solutions today. Thereafter, I will discuss about the developed adaptive out-of-step protection concept and how it works. Moving on from that, I will discuss the hardware-in-the-loop testing setup, after which I will show the testing results, and I will conclude my presentation with a brief demonstration of the developed algorithm. So let's get started. First of all, what is an out-of-step condition in a power network? Disturbances in the power network can propagate into a larger scale event, which will cause a major imbalance between the mechanical input and electrical output power of generators. This major imbalance can result in a loss of synchronism in the power system, and this is referred to as an out-of-step condition. During this out-of-step condition, large oscillations of currents and voltages occur, which cause additional mechanical and thermal stresses on the equipment that we have in the power network. As a demonstration of this, I have shown on this slide a current oscillation during an out-of-step condition from RTDS simulation. where we can see that the oscillations in current values can become higher than the actual fault currents at the start of the event here on the picture. So therefore, we need to have some sort of protection installed in the network that can detect the out-of-step condition and react accordingly. Which leads me to the protection part of this presentation. So for out-of-step condition, what type of protection is conventionally used? Today, the conventional out-of-step protection relies on impedance relays, which use the apparent impedance seen at the relay location to detect an out-of-step condition. How this is realized conventionally is that inside the impedance relay, two characteristics are built that the relay uses to measure the trajectory and speed of the apparent impedance change and determine power swing in the network. From this, the relay can distinguish between a stable power swing or a recoverable swing, as shown on the right-hand side figure, or an out-of-step condition, whereas the swing is non-recoverable. For this, the impedance-based protection devices require settings in order to function properly. And to compute these settings, the network should be well studied. To compute these settings for the impedance-based relays, we need to thoroughly run network simulations, and this is very time consuming, and the network should be well known for the settings calculation. With more renewable energy sources being integrated into the power system, the generator composition becomes harder to predict, and this in turn complicates the calculation of protection settings for the impedance-based out-of-step protections even further. So it becomes difficult to assess which type of generator composition should be used for the settings calculation and what actually to set as the values for the protection. So this made us think, how can we improve this? And we developed a new out-of-step protection algorithm using wide area measurements that does not require any settings or requires minimal settings. And we tested it using hardware in the loop simulations and compared it to the traditional impedance-based relays. So moving on to the developed protection algorithm, how does it work? So, as I mentioned, the goal was to develop an easily implementable out-of-step tripping algorithm which requires minimal settings and can adapt to different grid conditions in real time. And what we came up with is to try to rely on computation of system impedances as seen from the both ends of a transmission line, so that we can make the protection algorithm adaptable or to a different type of grid conditions. To do this, we compute the impedances on the remote ends of the transmission line using the following equation, where an equivalent impedance is calculated from two sampled values in voltage and current phasors using wide area measurements. How this looks in the actual algorithm is shown on the slide here, where the voltage values measured are shown on the left hand side and the current values on the right hand side. So both voltage magnitude and angle, and current magnitude and angle. And whenever there is a step change in the network or in the measured quantities as shown on the slide, the algorithm detects an event and therefore takes the T1 and T2 values and computes system impedance based on this. For this, there is a rolling buffer implemented in the algorithm that constantly refreshes and saves the T1 value, which, if an event is detected, is in the past, and it has to be stored beforehand. And the T2 value will be taken after the event ends. On these graphs, the blue represents the measured quantity, and the red and yellow show the T2 and T1 values of voltages and currents respectively. So in a sense, we try to take a meshed transmission network shown on the right hand side of the slide and represent it as a two machine equivalent situated around the protected transmission line. And in order to compute the actual source impedance or the network impedance at either end of the transmission line, we need to add a second measurement location to the algorithm, which usually is located on the load side or a load feeder, where we expect a step change to occur. This can be in a regular load, or this can be a switched shunt or a capacitor bank. And thereafter we use superposition criteria combined with the previously shown formula in order to compute the source impedance at the ends of the transmission line. And when we have acquired these source impedances, this then allows us to construct an equivalent phasor diagram for the equivalent electromotive forces behind these system impedances, which represent the inertia center voltages for the protection algorithm. From these system impedances, we then construct a power angle curve, and this is how the actual protection is then realized or based on. So we construct this power angle curve from the previously computed system impedances, and once we have the power angle curve on this, we can fix the last stable angle point by using the computed angle difference and the measurement values. The last stable angle point is limited to between 90 and 130 degrees to ensure that the computed last stable angle point will remain on the right hand side of the power angle curve. Then also the algorithm constantly monitors the angle delta between the two equivalent sources or the two computed inertia centers in the network using the measured voltage and current values and the computed impedances at the ends of the transmission line. The protection will operate when the criteria brought out on the slide are met. So the protection operates or issues an operation command when the computed angle difference delta is larger than the last stable angle value for two consecutive measurements, and in addition the derivative value of this angle difference needs to be positive for two consecutive measurements, so that the angle value is seen as increasing. So the system heads into instability. Additionally, there are safety checks incorporated in the algorithm in the form of voltage magnitudes and derivative being lower than a certain threshold value. The voltage magnitudes here need to be larger than 0.5 per unit, and this is set so just to check if the bus bars and the transmission line where the protection is implemented are actually energized. The derivative value of the angle needs to be smaller than 20 pi radians for 2 consecutive measurements, and this acts as a fault detection unit for the protection algorithm, so that when there is a fault in the network, there is a very high increase in the computed angle difference, but during a fault in the network, this protection should not operate. Therefore, this is used to block the protection operation from during fault events. Moving on to the hardware-in-the-loop testing setup. On this slide, we have the hardware-in-the-loop test setup we use to test the developed algorithm together with impedance-based protection relays. So on the left-hand side, we have the RTDS setup at TU Delft, and we used GTAO output cards together with a power amplifier to provide input values to the impedance-based protection relays, which in turn provided feedback to the RTDS simulator using the high voltage panel on the simulator. As for the developed protection algorithm, it was set to run in an external controller which receives C37.118 PMU data from GTNet X2 card and sends back data using IEC 61850 to the RTDS simulator. This setup has to be time synchronized, and for this our lab incorporates an atomic clock slave unit which synchronizes the RTDS and the external controller, so everything is time synchronized. As for the testing network used for the hardware-in-the-loop simulations, the IEEE 39 bus benchmark system was taken as a base, and to this we added wind power plants in order to investigate the protection's performance in different network scenarios. 2 testing cases are chosen to show the algorithm's performance in different network conditions, and here case study A, which is noted in red, represents power swings between 2 larger parts of the network, and case study B, shown in blue, represents a single machine to infinite bus type of scenario. Moving on to testing results. As the impedance computation part of this algorithm is essential for the algorithm's operation, the accuracy of this part of the algorithm had to be tested. So in order to test and validate the impedance computation part of the new algorithm, a simple 2-machine equivalent system was built with adjustable source impedances at either side of the network. And in this, multiple scenarios were run, and the errors of the impedance computation were investigated. The errors of the impedance computations are shown on the heat map on the right-hand side of the slide shown here, and we can see from this slide that the impedance computation part of the algorithm produces an error of about 4% on average. In some edge cases, the error can go up as high as 12%. This was found to be sufficiently accurate for the auto-step protection algorithm function, So we move on to the results of the out-of-step protection algorithm part testing. For the case study A, which represents swings between two parts of the network, we can see that the developed algorithm shows faster operation times than the impedance-based protection relays in all of the renewable energy penetration scenarios. In addition, it has to be noted here that the impedance-based protection devices fail to operate for 60% of renewable energy penetration scenario for the shorter transmission line between two parts of the network, whereas the developed algorithm operated successfully. As for the results for case study B, so representing a single machine infinite bus type of scenario, we can see that the developed algorithm and relay 2 show very similar operation times. However, the relay 2 fails to operate in multiple scenarios where the operation time is marked as 0, whereas the developed algorithm operates successfully. Before moving on to a short demonstration, I would also like to thank the contributors for this work, which is shown on the slide here. We are now in RTDS runtime environment, and we are running the IEEE 39 bus test network to demonstrate the algorithm's performance and compare it to the impedance-based protection relays. In the network, the protection algorithm is installed on the transmission line between buses 14 and 15 and receives its measurement data from two PMUs that are located on the buses, respectively PMU 1 for bus 15, PMU 2 for 14. The impedance-based protection relays are located on bus 15 side of the transmission line. We will initiate an out-of-step condition by applying a three-phase fault on line 16-17, after which the line gets disconnected from the network and power swings take place in the transmission line remaining connecting to two parts of the network. First, I will switch the loads on buses 15 and 14 for the protection algorithm to compute the system impedances, which are shown here by the phasor diagrams. We are running the base case, which has 0% renewable energy penetration. So I will switch the loads now, and we can see that when I switch the load, the protection algorithm computes the system impedance magnitude and angle values that are needed for the protection algorithm operation. This is recalculated every time a step change happens in the network, so where every time when load is switched in the network. I will do this for the other side of the transmission line as well, and we can see that on the opposite side the impedance is also computed. Now I will create an auto-step condition on the protected line so that we can see how the protection operates and how the impedance-based protection devices operate. The fault created here between buses 16 and 17 is 100 milliseconds long. And from this diagram here, we can see that the algorithm is blocked during the fault event, and both of the sides detect an event in the network. Afterwards, when the generator angles start increasing, shown at the bottom here, the algorithm issues an operate command when the angle values go over the threshold value, or the delta value that is computed goes over the threshold value. The protection relays here in the bottom graph of this graph show an operate command as well. However, the relay 1 issues an operation command later than the developed protection algorithm, and relay 2 operates on the second swing in the network. To see the operation times here, the protected line was disconnected from the network by the developed algorithm almost 300 milliseconds faster than relay 1 and 1.2 seconds faster than relay 2. Therefore, the developed protection algorithm offers faster out-of-step condition detection. And with this short demo, I will conclude my presentation. Thank you for your attention. I have also set on the slide my email, so if we can not answer all the questions during the Q&A session, I will be happy to take any additional questions on my email. Thank you.
Thank you so much, Marco, for your presentation. And it was great to see a demonstration as well. And thank you, audience, for your questions. Please keep them coming as we welcome our next presentation. Our second topic is Power Hardware in the Loop System for evaluating physical electric vehicle onboard chargers using the RTDS simulator. Our presenter is Dr. Carl Ho from the University of Manitoba. Dr. Carl Ho received B.Eng and M.Eng double degrees in 2002 and his PhD degree in 2007 in electronic engineering from the City University of Hong Kong. In 2007, he joined ABB Switzerland. He has been appointed as scientist, principal scientist, and R&D principal engineer. In October 2014, he joined the University of Manitoba in Canada, where he currently holds positions of professor, associate head of the Department of Electrical and Computer Engineering, and Canada Research Chair in Efficient Utilization of Electric Power. He established the Renewable Energy Interface and Grid Automation Lab at the University of Manitoba. He is currently an IEEE senior member and serves as Associate Editor-in-Chief of the IEEE Journal of Emerging and Selected Topics in Circuits and Systems. He's an Associate Editor of the IEEE Transactions on Power Electronics and the IEEE Journal of Emerging and Selected Topics in Power Electronics. He received the 2018 TPEL Prize Paper Award, the Journal of Emerging and Selected Topics in Power Electronics Associate Editor Award, and his student project team received Best Student Team Regional Award of the IEEE Empower a Billion Lives 2019 competition in the Americas region. Please welcome Dr. Carl Ho.
Good morning, good afternoon, good evening. I'm Carl Ho from University of Manitoba. It is my pleasure to give a presentation in RTDS User Spotlight Series 2.0. Today, we will discuss about how we can use a RTDS-based power hardware in the loop system to evaluate commercial electric vehicle onboard chargers. The talk will be given by me and my former PhD student, Dr. Isuru Jayawardena. Currently, he is a HVDC specialist at Hatch, Canada. In this presentation, we will firstly define power hardware in the loop and have a look about power electronic system in electric vehicle, specifically EV onboard charger. Afterwards, we will explain the conceptual idea of a power hardware in the loop system for evaluating EV chargers. Also, we will show some experimental results to verify the overall system performance. And finally, we will conclude the presentation and discuss about future research work in our laboratory related to this presentation. Modern power electronic systems are getting popular in power system applications. Example, solar energy requires PV inverter to inject power to the grid network. If scientists, researchers, or engineers want to simulate power electronic system with power system network in real time, we can use a real-time simulator to model the power electronic systems and the network. All the models running inside the real-time simulator. For this particular system, that is RTDS, you just need to draw the system in a software called RSCAD. Using this system, you can measure the signal in real time through digital to analog card externally. If you want to design a control system in external control hardware, example FPGA, DSP for the power electronic system, you can use the configuration of controller hardware in the loop simulation. Since RTDS provides real-time signals, converter is simulated in RTDS and gives feedback signals to the controller, and then provide PWM signals from the control hardware to the converter inside the RTDS. Thus, we call this one as controller hardware in the loop. The last one is power hardware in the loop. Physical power electronic systems are connected externally to a simulated power network in the RTDS. The converter is running in full power, but interacting with the real-time simulator. Somehow, it looks like a virtual reality system. The physical power electronic system does not know it is working in a simulated environment. This kind of testing platform is very promising for converter manufacturers to have a full power evaluation for their products before going into market, and it is also useful for utility company to evaluate grid impacts before any physical installations. There are three different types of hardware in the loop real-time simulation for evaluating power electronic system in real time. As you know that an electric vehicle, there are some critical power electronic system. Basically, they are connected to battery pack. The first one is traction control unit, or say motor drive. It sources energy from the battery pack to drive the motor, and then the car can be moving forward or backward. The second one is an onboard charger to source power from our grid network and charge the battery. And there is also an auxiliary power supply to power up the electronic device in the car. Externally, EV can connect to a DC fast charger to charge up the battery quickly. We can see the critical electrical elements for power electronic system are battery pack, motor, and the grid network. In this presentation, we will focus on onboard charging system. It means in between the battery pack and the grid. A commercial EV onboard charger is shown in this picture. Typically, an EV charger includes 2 to 3 power stages. The first one is AC to DC power factor corrector because it has to satisfy IEEE and IEC standards for the input current quality. The second one is isolated DC-DC converter to provide galvanic isolation for safety purpose. And the third one is a DC to DC converter to charge the targeted battery. Usually, it is a single power direction from the grid to the battery. If the charger is equipped V to G function, all power electronic stages have to be bidirectional. If we want to connect the commercial EV charger to a simulated environment, we need to have a RTDS, and we should model the grid and the load and the battery in the software in the RTDS. But the EV charger is modeled as a black box in the software. In the hardware side, the EV charger connects to 2 amplifiers. They emulate the battery and the grid. The voltage values of the emulator are follow the simulated values in the software. It means the hardware and the software are exchanging information. The EV charger is running at full power, and the EV charger is thinking it is charging a battery and sourcing power from the grid. Such kind of system is good for burn-in testing of EV chargers since the power is circulating in the loop. It only sources a little power from the real power source for compensating the loss in the whole system. It also can test the function of EV charger, for example, protection. In the grid side, power quality can be studied with a simulated grid network. In the DC, that means battery side. Battery model is in RTDS and it connects to a voltage control current source. And the current source emulates the DC terminal of EV chargers in the software simulation. The battery voltage signal becomes the voltage reference of output voltage of the amplifier. Thus, the EV charger looks like connecting a battery. Similarly, the grid network is in software but interacts with the charger through the amplifier. Of course, there are analog to digital and digital to analog converters to connect the hardware and software. So on this page, you can see that we have a physical grid and then connecting to a EV charger. For this physical system, basically you can model a EV charger as an impedance, ZDUT, and also the definition which is equal to V over I. Besides, this V charger is modeled by an impedance. The grid source also can be modeled by a voltage source with an impedance. That is the Thevenin theorem. Now we have an equivalent circuit, a voltage source, an impedance that represent a grid voltage, and also an impedance modeled as a EV charger. And now we can separate these two equivalent circuit to two sections. The grid that is simulated inside RTDS, so that means that will be implemented in the software RSCAD. And the EV charger will be a physical device, a commercial system, so that's why it will be a hardware. In between these two networks, we can have some devices to connect them together, including digital to analog converter and also power amplifier to amplify the signal inside the RTDS and then provide real voltage to the hardware. And also there is a feedback. It sends the grid current from the hardware, and then there is analog to digital converter to put this current signal into the software. We also can use a voltage type ideal transformer method, ITM, to represent the system here. Inside the software, and there is a voltage source and an impedance. And the software provides the grid voltage signal through the amplifier and then provide it to the hardware. And then you also can see that to sense the current and then feed back to the software. And inside the software, there will be a voltage control current source to represent the EV charger inside the software. In the DC battery side, the power hardware in the system is quite similar to AC side as well. Inside the software, we have a battery model, so that means we do not have a physical battery. For the hardware, the same, we can model the charger just using a simple impedance. If you take a look about the interface, you will see here the same. We have a analog to digital converter and then put it to an amplifier and then also sends the current from the charger and then feed it back to the software. In the hardware, amplifier is emulating a battery, and in the software, a voltage control current source is emulating the EV charger. And this battery, it can be different types of battery, and then for this study we use lithium-ion battery inside the RTDS. There are two amplifiers in the system. At the AC side, the AC voltage is in high frequency and also change all the time. So that's why we need to use linear amplifier, because a linear amplifier, it can give a very high bandwidth. For the DC side, we use a switch mode amplifier we developed by ourselves. It is a very simple bidirectional buck converter. And here, that is the simplified control block diagram. The signal of the battery voltage, that is from RTDS, and this reference voltage guide the output voltage of the buck converter using a PI controller go through the whole system here. So that's why we can use this bidirectional buck converter to amplify the battery voltage signal. And using this power electronics amplifier, it can provide the advantage of high power density, low cost, and also high efficiency. And also because the battery, the voltage, it doesn't change very fast. So that's why we can use low bandwidth controller here and also using power electronics amplifier. On this page, you will see that we will have a very simple experimental result to show you how the DC battery emulator it works. So this one, that is the power electronics based battery amplifier. Because this amplifier, it emulates a battery. So now we are testing when the battery is being charged. So that means the power direction, that is from the current source here to charge the battery emulator here. And this voltage, that is controlled by RTDS. That means the lithium-ion module that is inside RTDS. But the physical power that will go through this bidirectional emulator to go to the DC load. Of course, it will connect to a grid and then come back to this current source. You can see here on the measurement. So the first one, that is the software. We took the data that is from the software, that means from RSCAD. And then the second one, that is also from RSCAD as well, but that is for SOC. And the last one here, that is a physical measurement at the terminal here, including the battery voltage in blue color and also the battery current in red color. You can see here the external measurement that is very close to the software data. And also because it is a current source, so that means providing a constant current to the battery emulator. So you can see here there is a 8 amp current providing to the battery. So that's why the battery voltage is going up in this way until we stop the testing. And also in the software internally, you also can see that that is going up as well. And you can see that the SOC is increasing until it reaches 100%. We did another test that is for battery, which is discharging. So that means releasing energy to somewhere. We put an electronic load here to source energy from the battery emulator. So that means from the model inside RTDS. And it is also a constant current as well. That's why you can see that the battery voltage is dropping, because now the battery is releasing energy, and also the SOC showing that in time, and then it will go to 0% from 100%. On this page, you can see now we are using a physical battery charger. So that is from Delta Q, and it is 1.2 kilowatt battery on board charger. This one is a block diagram. We need to use two amplifiers. One is for AC source, another one that is for DC, that means the battery. And here you will see that for the grid side, the emulator will use the linear amplifier connecting to the battery charger, and the battery side, DC side, we use a power electronics emulator, and then both of them connecting to RTDS. And you can see the laboratory setup here, the charger, RTDS, A to D, D to A cards, linear amplifier here, power electronics amplifier, and also the RSCAD to provide models to RTDS. Again, so this AC source, they are common. So that means the power that is from this source to going through the battery charger and also battery emulator, and then coming back to here. So that means the power is recycling in this loop. So here is the experimental result, and also you can see the battery DC side behavior. In the very beginning, so that means the SOC was around 25%, and there are two very well-known charging stages. The first one that is constant current charging, and the second one that is constant voltage charging. That is the built-in function inside the commercial EV charger. In the beginning, when the SOC is not high and the onboard charger is providing a constant current charging function until it reached around 68%. Now you can see that the voltage before that was increasing, and then until it reached this point, and the voltage will keep constant and providing constant voltage charging, and the current which is increasing until it reached 95%, and the EV charger will stop charging the battery. You can see here in the software and the hardware, basically the data, they are identical. In the AC side, because an EV charger is required to fulfill industrial standards, so that's why the current of EV charger which is in phase with the voltage, and also it is sinusoidal to create the power factor equal to 1. So that means there is a PFC, power factor corrector, as a P-regulator in the EV charger. So the AC voltage that was from the linear amplifier, and also it was from the software inside RTDS. If you see the AC side and also DC side on the same page, so you will see that in the very beginning, when the battery was quite empty and the charger providing a constant current charging mode to charge the battery, and the voltage of the battery which is increasing, and also for the AC side, the current here, the amplitude is larger to provide higher power to charge the battery. And if you zoom in this time slot, and then you will see that here is the AC voltage, here is the grid current for the EV charger. But until it reached around 68% SOC, and then it changed it to constant voltage charging mode. So that's why the battery current which is increasing. And also you also can see here to zoom into the AC side, and the amplitude of the input current is reduced. So here that is the full picture to see the whole charging period for the DC and AC side behaviors. We also can use the power hardware in the loop systems to study some power quality issues. For example, here that is one case study. So when the grid voltage it decreased from 120 volts to 92 volts, so that means there is a voltage set for around 10 cycles, and the EV charger increased the grid current to maintain the more or less constant power to charging up the battery. When the voltage returned to normal and the EV charger, the control loop will reduce the input current to maintain the same power as well. If we put a longer period for the voltage set, that means it becomes under voltage. So the grid voltage is from 120 volts to 78 volts here. And in the beginning, the EV charger tried to increase the input current and then maintain the input power to be constant to charge up the battery in a constant power mode. But after 20 cycles, and then the EV charger is stopped charging. The reason is now you have a very high current going into the EV charger. It will create very high conduction loss for the semiconductor. So that's why the EV charger, it decided to turn off the system, and you can see here that there is no input power anymore. It also can test with a very complicated grid network. For example, here that is a weak grid with PV power change. So we can simulate a grid network in the software side. So for example, here the grid with a very large inductance, and also we have a PV energy source to inject power into the grid. Then the hardware will have interaction with the grid here. So this one, that is the model inside the RSCAD, and we have a terminal connecting to the hardware through RTDS. Now you can see here, so in the very beginning, the grid voltage, it keeps constant, 120 volt. When the PV plant reaches providing 10 kilowatts to the grid network. But when the PV suddenly drop the power from 10 kilowatts to 100 watts only, and then the grid will become very weak because you have a very large inductance here and the EV charger is drawing power. And so that's why the voltage of the EV charger, it drops because of loading effect. And also the EV charger, the current is increasing and also the voltage that is decreasing to try to keep constant power. So you can see that there is an interaction between the hardware and also the software. And of course, until the current keep around 20 cycles and the EV charger is stopped charging the system and go into the protection mode. I have mentioned there is another power electronic device in an EV. It is traction control unit. It also can be tested using power hardware in the loop with RTDS built-in battery and motor models. The details can be found in the ECC 2021 conference paper. Conclusion: Power hardware in the loop creates a flexible testing platform to evaluate EV onboard charger using virtual reality approach. All the elements connecting to the EV chargers are real-time simulated, but it gives a full power test for the EV charger with practical results. Types of battery, grid conditions, and fault scenarios can be modified by a few clicks in software. It saves energy during commercial product burn-in tests with condition changing, and also further power quality and V2G function will be easily studied before doing any real installation. There are other suggested IEEE journal papers which explain power hardware in the loop in details, including stability analysis and compensation of system delay time. And also, we would like to thank Rigolab members and supporting organization. We believe that we could not achieve that result without their contributions. Thank you very much for your kind attention. We welcome any questions related to this presentation. Thank you.
All right, thank you everyone so much for attending today and for your questions during the presentation. I hope you can hear me okay. I just wanted to start our live Q&A session with a quick note. I didn't actually introduce Isuru Jayawardena during the second presentation, and he worked with Dr. Ho on that, so I wanted to give a brief summary of his bio before we get started with the questions. Isuru received his BSc degree in electrical engineering and his diploma in energy technology from the University of Moratuwa, Sri Lanka in 2011 and 2015, respectively. He recently completed his PhD degree in electrical engineering from the University of Manitoba, in which he worked on developing power hardware in the loop testbeds for microgrid and EV applications. He worked as a research assistant at the university's Renewable Energy Interface and Grid Automation Lab, and he's currently an HVDC specialist at Hatch Limited in Winnipeg, where his current focus is on HVDC and FACTS projects, including renewable energy integration and power system planning studies. So thank you very much, Isuru. Okay, let's get started with some of our questions. I'll start with a question for Marco. We had a couple questions on communication delays and non-determinism of communication channels. Did you want to talk a little bit about how you address these concerns?
Yes, thank you for the questions. When we use wide area measurements for anything, of course, communication becomes a topic, and we need to address the delays and the issues related to the communication. So what we did since we did our hardware-in-the-loop testing in the laboratory, where the latencies in the network are not very high, but we still wanted to represent kind of a real installation scenario. So we included a artificial delay in the controller itself, which is named as a wait time. So the controller has a 100 milliseconds wait time implemented in there to wait for collection of measurements from the power network. And after that, the measurement data is going to be processed by the algorithm. So just to address the delays and the non-determinism of communication, we have included a time delay inside the algorithm so that we can get aligned measurements from the network. And then after the algorithm operates. So all the results already incorporate this 100 millisecond time delay. And when, for whatever reason, this measurement time delay exceeds this wait time value, then the protection is going to be blocked because we cannot then make sure that we are getting accurate measurements from the network.
Excellent, thank you. Let's move on to a question for Carl and Isuru from the University of Manitoba. You talked about your use of both linear and switched mode power amplifiers in your power hardware in the loop interface. And we generally have a lot of interest in the differences between these types of amplifiers and the criteria for selecting them, the bandwidth and response time, and when it's appropriate to use these types of amplifiers. So I wonder if you could elaborate a little bit on the selection of these amps and how they worked in the interface.
Hi, I can touch base on that. Here, the idea is to, in this project, we were emulating the AC grid and also the DC battery. So for the AC grid side, we use a linear amplifier because AC, when you emulate in the AC grid, if you want to emulate the normal 60 hertz signal with harmonics, so you need to have a higher bandwidth amplifier. So the linear is typically have fast dynamic characteristics than the switch mode. So on the battery side, you have battery side, the battery itself is a short dynamic source because its responses are in the seconds range. So in that sense, switch mode amplifiers we used. Hope Carl might, if Carl want to add something, you can add it, Carl. Hi.
No, you answer very well. Thank you, Isuru.
Yeah.
Excellent, thank you. All right, a question for Marco. In inter-area mode, there's no concept of mechanical power that remains constant during a fault, similar to equal area criterion. How has this been addressed?
Yeah, that is a very good question. So if we have oscillations between two parts of the network, then we indeed cannot have a concept for mechanical power in this case. And it has been addressed, or we consider this case in a way where we monitor the pre-event active power flow through the transmission line, and we take this pre-event active power flow as a input for the mechanical power flow or for the power imbalance between the two areas. So this is used as a kind of a replacement for active power or mechanical power input in this case, where there are swings between two parts of the network.
Great, thank you. And I think we'll move on to our last question before we wrap things up, also for Marco. How does the algorithm perform when the amount of generation in service at each end of the system changes, as is very common in the real system? And how did you mimic that?
Yeah, that's also a very good question. So we were trying to address this as well by changing the renewable energy penetration scenarios during our testing to see how the algorithm's performance actually changes when we change the renewable energy penetration scenario as well. So that's why we have done sort of mass testing with different types of renewable energy penetration levels to see how the algorithm copes now with the changes in the generation scenario. And when we look at the results, we can see that the developed algorithm copes with this quite well. It provides still very secure operation when we compare it to the existing impedance-based solutions, which from certain scenarios, for example, do not operate at all.
Excellent. Thank you, Marco. I think that is it for our questions for today. So thank you so much, everyone, again for attending. We look forward to seeing you on our next webinars. So keep yourself posted on those by subscribing to our mailing list. And you can download the slides for these presentations right here in the additional materials widget. And of course, you'll be able to access this recording after the fact as well. So thank you again to our presenters and our attendees, and I hope everyone has a great day.